is actually the first in-person seminar I've introduced in a while, so welcome everybody. Thanks for attending. It's actually a really great pleasure and honor for me to introduce Jason Wheeler from Sandia National Labs here today. I've actually known Jason for about 9 years because I worked with him as a postdoc at Sandia. He was one of my postdoc mentors. Jason comes to us by way of a bachelor's degree at Brigham Young University. Then he did his master's degree at MIT with Neville Hogan. And then he did his Ph.D. at Stanford with Mark Kutkoski. So in my opinion, it's pretty hard to come up with a resume that's as diverse and as impressive as that. Since then, or actually throughout that process, Jason's been a staff member at Sandia National Labs, and I think it's called the Robotics, Counter-Robotics Research and Development Group now.
That's as right as I can.
Sounds good. And so he's been there where he leads a large portfolio of different robotics projects. He's actually a distinguished member of technical staff, which is one of the highest ranks one can achieve there. And his portfolio has included projects with both internal and external customers, DARPA, CDMRP, which is congressionally directed medical research programs. And so he does a lot of really interesting work, both in traditional robotics and wearable sensing, biomechanics. And I think you're going to get a nice overview of a lot of cool research today. So I'll kick it over to you, Jason.
Thank you, Ani. Appreciate that kind introduction, and it's an honor to be here with you all. Appreciate the opportunity to talk a little bit about some work that I'll talk a little bit about Sandia and our group and what we do, but primarily I'm going to talk through some of the, we're a robotics group at our core, but my interests kind of come, as Ani alluded to, from a little bit more of a biomechanical perspective. So I'm going to talk primarily about projects that sort of meet at that intersection of robotics technology and musculoskeletal biomechanics. And then I'll kind of branch out a little and give you a little broader picture of the group at Sandia and sort of what our interests are. Just a couple brief words about Sandia as a whole. So we're a federally funded research and development center, which is a word soup that basically means we're a national laboratory affiliated with the Department of Energy. We have a broad portfolio of programs across defense and energy and other national security type missions. We have science and technology and micro and nanotechnology. We have a pretty good size, I think one of the bigger robotics research groups in the government complex. Johns Hopkins Applied Physics Lab has a robotics group, as do a few others, but I think ours is at least as big as any other robotics group in sort of the government complex. So with that, let me kind of just jump in here to some of the things I want to talk about today, and I'll circle back at the end to some of our broader robotics portfolio. But I want to talk a little bit about, my understanding is primarily a robotics-focused audience here. I'm going to spend a few minutes talking about biomechanics, which will be familiar material to many of you, just to sort of set the stage for some of the projects that I want to talk through. So some of those include, I'm going to talk about motion training with some haptic devices. I'll talk about performance and injury reduction. Some of the work I did in graduate school related to proprioceptive feedback for prostheses. And then I'll talk about a little bit more prosthetic socket related work and some current work we're doing to look at injury reduction and prevention for industrial workers with Georgia Tech, actually. So first of all, just wanted to briefly touch on why should we study human movement? And first of all, it's just fascinating, frankly, to me, that I can stand here and with very little cognitive effort do all kinds of complex motions with my limbs and fingers and things. And as roboticists, I think in particular, this sort of is not intuitive. It's like, well, how can I with so little thought and effort do all these highly coordinated motions? And for many years, we've tried to replicate that in robotic systems, of course. And it's been the inspiration for a lot of the work that we do in robotics. But there's also many specific applications that we can improve people's quality of lives. Certainly for sports and performance. There's military applications, and then there's a lot of applications to public health, including rehabilitation and restoring lost function to those who have some kind of pathology. So just briefly, and I won't dwell too much on this, I just want to talk about a very oversimplified model of human movement from the forward direction. So we have some command that the brain sends down through the nervous system to muscles that have their own internal dynamics in the way that they generate force and motion. And then those muscle forces and motions are imparted on the body through different geometrical moment arms and things on the skeletal system. And then we go through our normal dynamic equations of motion to produce the actual output kinematics. And then there's some feedback that occurs along the way. So I'm going to just talk briefly, very briefly, about sort of each of these just to give a little bit of context. So first, as we have this neural command that goes down to a muscle, the muscle, just like any other actuator, cannot instantaneously generate force or motion, but there are some dynamics associated with that. One simplified but useful model of that is kind of demonstrated here, where we have a parallel elastic element here and a series elastic element in conjunction with this contractile element that it's called. And it produces these sort of two phenomenon. One is sort of a length force model, where depending on the level of activation, the amount of force produced at the muscle is a function of its length at any given time. So that if you include the tendon in that, you get this sort of green line here that has both as a function of its length, you can generate different amounts of tension if you include the tendon versus if you exclude it. The other interesting part is if, depending on how fast I'm trying to move, I can get a different level of force, as is true with most robotic actuators. And this, for instance, is, as you would expect, as you move faster, the amount of force you can generate decreases. And if you take the speed time, the velocity times the force, you can get power. And what you see here is sort of a peak at about a third of the maximum speed of the muscle. So this is, for instance, why your bicycle has gears, right? Because theoretically power is the thing that makes you go, right, at a particular speed. And theoretically you could go at a very low speed at a very high torque, or a very low torque at a very high speed. But it turns out that elite athletes tend to pedal at about this 1/3 maximum shortened velocity speed. And this is, again, like if you're trying to be efficient with your robotic actuators, you might do something similar to try to operate it at a good speed. But that's just a little background on the dynamics of the muscles. And I won't spend much time talking about this, but the geometry associated with how those muscles produce joint moments is fairly complex. You often have many more muscles than degrees of freedom at a joint, and so you have sort of an overactuated situation. Those moment arms in general are not constant with joint angle, so as you move a limb, your ability to produce torque at that joint may change because the moment arms are also changing. So that needs to be taken into account if you want to actually study the joint dynamics. And then, of course, you can do, once you have those joint torques, you can do your normal Newtonian or whatever other modern dynamic method you want to generate to create these equations of motion. And of course, you'll want to analyze the contact forces with the environment as well. So that's just a very simple overview. In practice, the way we actually study human movement is sort of the opposite of that, where we do this inverse approach. Because we can't measure the muscle forces or the neural activations with any degree of ease. And so instead, we measure the motions, which we can do with cameras and other types of systems, and we measure the contact forces with the environment, and then we go backwards. And so we can measure position data from these marker-based camera systems. We can take derivatives of those to get to accelerations and use our equations of motion to get torques at the joint. That's called inverse dynamics. And then from there, if we want, we can go one step further and try to figure out the muscle forces. As I mentioned before, we have more muscles than joints, and so that's a non-trivial problem. You have to have some kind of minimization function to be able to feed into that, or some other approach that makes some assumptions about what the brain might be doing to modulate which muscles do what at any particular time. But there are methods that have been attempted for that. You can estimate muscle forces with EMG sensors and other things, and that works for certain muscle groups. So how do we make these measurements? The picture here is from Professor Young's lab, just here nearby. I haven't been there yet, but it's here nearby, I've been told. So we have all kinds of different measurement systems, a camera-based kinematic system that measures the position of markers on the body, all kinds of instrumented force plates across the lab to measure the interaction forces with the environment. And this is sort of the gold standard of how we analyze human movement. There's a lot of advantages with it. This is sort of, you're doing research the way that you often want to do that. Of course, the limitation is you can only sort of do that in a laboratory with all this equipment. There might be some situations where you want to do something maybe not quite as accurate, but a little more flexible. And so people are now developing wearable systems that can be taken anywhere. There's IMU-based kinematic sensors that are available. The main limitation of that, well, their accuracy is certainly not what you would get with a camera-based system. The other big limitation is there's not an easy way to get the force data that you would get in a motion analysis laboratory outside of a laboratory, which is why I want to talk briefly about one of our developments that Professor Mazumdar actually worked with us on, and that is, can we build an insole that can give us something that approximates this ground reaction force? So the ground reaction force that you would get from a plate in your lab has XYZ force, XYZ moment, and center of pressure, which is the point of application of the ground reaction force. In order to do our inverse dynamics and other things we want to do to analyze human movement, we really need at least all three components of the force and the center of pressure. We might be able to get away without the moments in some cases, but we definitely need those 5 pieces of information: X, Y, Z force, and X and Y center of pressure. The Z center of pressure is trivial. It's in the plane of the ground. So in order to do that, you have to have some kind of sensor in your insole or other sensing medium that can measure not just the normal forces, but some shear forces, because you need those medial lateral and anterior posterior forces as well. And so we've developed this optical sensor, which is embedded in silicone, that looks something like the picture in the upper left here, where on the edges of this white reflective square, we have pairs of emitter and detectors, optical emitter and detectors. These are ICs that are often used for proximity detection in assembly and operations and things like that. So we put a transparent layer of silicone, which is sort of our dielectric layer, and then we put this opaque layer above it, which has this reflective square surrounded by a black absorptive medium around it. And what that does is now when I apply a shear force to this, say in the horizontal direction, the signal on the sensor on the left is going to drop because I get more black and less white. The signal on the sensor on the right is going to go up because I get more white and less black. And the ones on the vertical edges should not really change in that situation. So we get a shear measurement out of this, and we've done some preliminary studies on force plates to say how well does this do, and it does a pretty good job. So on the left here you see the center of pressure measurement we get from that, and it matches the force plate fairly well. And on the right we have the X and Y, the more difficult components of the ground reaction force, and then the vertical components of the ground reaction force on the right. It should be noted our sensor is not as good at picking up normal forces as it is. It's a little more sensitive in the shear direction, so we've added some pressure sensors in there to give us a little bit better normal sensitivity, which improves our Z direction ground reaction force and our center of pressure measurements. But this is some of the technology that we've been working on to move some of this biomechanical analysis outside of the laboratory environment. So I won't spend much time on this. I just want to kind of show what do we get when we do all this data analysis. We put somebody in a motion lab and we collect all this data. What do we get? And this is an example of how it's often analyzed. You'll get, this is just sagittal plane. So this is this plane looking from the side this way. I can get an angle at the hip, knee, and ankle, for instance. I can get a moment, and I can get a power by taking the moment times the derivative of the angle. And we can often look at this and learn things. So in this particular graph, which I just pulled from a paper, it's comparing older and younger individuals. And you can see some of the things that might change as people age and lose. In particular, the thing I was interested in at the time is what was happening at the ankle when they do a push-off. And we noticed that the power they were able to generate was decreasing as they got older, and we were looking for ways to potentially augment that. Another way you can analyze these data is by looking at the angle versus the torque, and you can sometimes infer interesting information from that. So I've shown the ankle again here on the right, and I've done this at 3 different walking speeds. And what you see is in the middle, when people kind of walk at their self-selected speed, that the ankle looks a lot like a spring, where there's really no internal loop associated with that. And so if you're designing an assistive device, for instance, you look at this and you say, or a prosthetic ankle, for instance, you could say, well, that just looks like I could just put a spring in there and get something similar to that function out, right? And people do that. A lot of prosthetic feet you see are just passive springs, right? But when I want to walk fast or slow, you see there's these loops, and that means there's energy imparted or absorbed by the system. And that implies, okay, I need some mechanism to do that if I want to not sort of impede the person. And so I just point this out as, if you're designing a prosthetic, for instance, it's often easier to do something that works at kind of one nominal task. If I need it to be diverse, it becomes much more difficult. Then I'm going to have to add actuators and control systems and other fancy things to be able to accommodate that. All right, let me switch gears a little bit and talk about some of the specific projects that we've worked on. Let me pull my phone out just so I don't talk too long. So one of the things that we may want to do is when people have movement disorders or want to improve their movement for some particular task, we may want to have a way to train them to do that. And so mostly in graduate school, a little bit at Sandia, I've worked at ways to provide some motion feedback, mostly with haptic devices. One example of that is for individuals with medial compartment osteoarthritis. So what this means is the cartilage on their knee is wearing out mostly on the inside more than the outside. And that's generally associated with this net torque on their knee called the knee adduction moment. And we can't measure easily the force on the cartilage or the internal moment in the knee, of course. But we can measure these external moments with the methods I described previously. And it's been correlated, and it looks something like this. You get a peak this is during the stance phase. You get a peak and then a second peak. So you get a peak when you load it and another peak when you push off, basically is what that looks like. And we can measure this in real time in our gait labs. And so a study that we did several years ago was have folks walk on a treadmill, and we're measuring this knee adduction moment in real time with the markers on the leg and the force plate in the treadmill. And then we gave them feedback of this knee adduction moment and said, hey, this is a thing you should try to reduce the progression of your osteoarthritis. And we didn't necessarily tell them how to do this. We just gave them feedback of this moment, something you don't normally have a sense of. We gave them a sense of it and tried to see if they could reduce it through sort of biofeedback. And in fact, they could. So this is the percent reduction after, we kind of let them choose how long, but it's not a long study, maybe 30 minutes or so of walking on a treadmill at most. They were all able to reduce their moment. We gave them feedback in one of two ways. For some, we gave them visual feedback on a monitor in front of them. For others, we gave them a vibration feedback on their arm. And they both were able to make those reductions. This is a kind of a summary of those results, which I won't go through in detail. I'll just kind of skip over that for time. But then one thing we did to expand this was the study I just described is what I would call implicit feedback, where we didn't tell them what to do. We just gave them a sense of something that they didn't normally have a sense of. You could be a little smarter, potentially, and give them specific feedback about how to change their gait based on a model of, as they change things in their gait pattern naturally or deliberately, we can see which of those, how those affect this knee adduction moment, and then give them specific feedback in which ones are working. And that's what we did in this study with different individuals on trunk sway and foot angle were two of the things we looked at. So tibia angle, foot progression angle, and trunk sway were the three things specifically we gave them feedback on. And what we found is they learned a little bit quicker if we did this. I think implicit feedback worked pretty well, frankly, because everybody's different, but this did allow people to learn more quickly and have a little better average total reduction. So one of the things I just want to mention is we did this in a expensive gait analysis laboratory with a expensive treadmill and all kinds of other equipment. In practice, for this to work, what you'd like is somebody able to walk around and have this feedback sort of chronically, because this is a chronic disease, this osteoarthritis. And in order to do that, you need some way to measure this. I'll just jump back quickly. thing we need to calculate is this cross product here. So it's a position vector from the knee joint center to the center of pressure crossed with the ground reaction force. So we need to be able to measure those two things. The position vector we can get from IMUs maybe, or some other sensor. The ground reaction force is what we're hoping our insole can provide. And then you can make this a chronically wearable device. Just briefly want to mention a couple things without going into too much detail. Several years ago, we're working for the Department of Defense on a program related to soldier injury and fatigue reduction, and proposed a system that included these adjustable ankle braces. So the application there was paratroopers. They jump out of these airplanes really fast and they kind of tuck and roll, but they have a lot of ankle injuries. They give them ankle braces that are almost like ski boots. They're so stiff you can't walk in them, and they hated them and never wore them. So we were trying to develop a brace that would stiffen up for the jump and then sort of immediately unstiffen. And we built some prototypes of that, as well as a device that imparted some energy to the ankle at each step. And there's now commercial devices that do something similar to this, but this was 10 years or so ago. But a couple of the interesting things I just wanted to point out about that particular project is we did some musculoskeletal modeling of this drop landing situation. Here we're modeling landing on a tilted platform, and we're looking at the ankle, the right ankle in particular, these ankle inversion issues. And we're adding ankle braces to the model and trying to see how that affects the amount of ankle inversion associated with these kind of landing. And so these tools, OpenSim is a open source biomechanical modeling tool that's widely used now in the biomechanics community. I won't talk too much about those results. Let me turn the volume down a little. So the other thing we did is try to characterize the impedance of the ankle. So this is with our collaborators at MIT. They have an ankle exoskeleton device that they're essentially doing system identification of the ankle at different points of the gait cycle. So they're applying perturbances with this ankle robot and trying to measure what is the impedance, mechanical impedance, stiffness, damping, and inertia of the ankle at these different points in the gait cycle. And so this is a really unique, I think, method and technique that you need a robot to do, really. And we were able to show at mass, damping, stiffness, at different points in the gait cycle. And you can see people kind of early stance phase, they add more damping and more stiffness. So this is early stance, terminal stance. These are different points in that cycle. And you can kind of see how people are modulating with their muscles those forces. And this was to inform our ankle brace designs. Okay, switching gears again to a different topic. So let's see. Just remind me, this ends at 1:15, right? So I want to probably wrap up around 1 o'clock. Okay. Another common problem with amputees, so that if you lose an upper limb, for instance, and you want to be able to provide some restored function, there's a few different ways you might control, a robotic arm that replaces a normal arm. And arms in general, much more difficult to replace than legs, because 90% of what I do with a leg is walk on it. I can't say anything similar with an arm. I do all kinds of things with it. And many people reject a prosthetic arm. It's very, very common for people to say this isn't worth the trouble. One of the common complaints is they don't have a good sensation of where the arm is in space. That's called proprioception. And so we did some studies to look at how could we potentially provide a sense haptically of this proprioceptive feedback. So one method that we explored used this rotational skin stretch device that can be applied here. It was placed near the tricep. You could put it, depending on the situation, in different locations. You had 2 pieces of double-sided tape, basically, kind of adhere it to the skin. I'll be perfectly clear, it's not the most comfortable thing, but we're testing whether or not this method was effective in conveying motion and position information of a joint. So in this case, say the elbow. So we're simulating transhumeral amputation here, where somebody is moving an elbow joint with EMG sensors on their bicep and tricep muscles. So we've essentially immobilized the elbow to simulate that. by having them pull up or down on this handle. So pulling up stimulates the bicep, pushing down stimulates the tricep. We pick up those signals, and we move a virtual arm on the screen. And so, we go through some, I won't talk too much about all the dynamics of that, but we model the dynamics of a prosthetic arm, we process the EMG data, and then we also have to feed this into the skin stretch device to figure out how to map the joint angle to, and it's a little bit of a nonlinear mapping, as you see there, just because we found from other studies that people's sensation was not directly linear related to the angle of that skin stretch device. So we did two different tasks. The first one was, if you see the picture in the upper left, we would have the arm start at one of the marked locations, and then we'd give them instructions to move at some distance, some number of degrees in the positive or negative direction. And what we're testing here is, and we gave them training before this, so they had a model of the dynamics of the arm in their head because they'd been able to see it move around. And then we're telling them, okay, now without any feedback, I want you to move from point A to point B, and we're going to measure how, and then hit a button when you think you're there, and we'll measure how accurately you did that. And we did this with and without the skin stretch device, so basically purely feed forward versus with this kind of crude feedback channel. And to give sort of a best case baseline, because nobody, even physiologically, I couldn't do this perfectly, right? We provided a kind of a control case where we put their other arm, their contralateral arm, in a manipulandum that mapped the position of the virtual arm, just to give kind of a best case situation. And here's what we found. When you gave, this is the error associated with the targeting. On the left, average error was 16 degrees or so with no feedback, went down to 10 or 11, 12 degrees or so with the skin stretch feedback, and the best case with the contralateral arm was in the 7 or so degrees. So we were closer to the best case than we were the no feedback case with the skin. So this seemed to show that there's some merit to this approach. And was somewhat promising. The other task we wanted to get some measure of sort of whether or not this device would lower the cognitive demand of using the arm somehow, and that's really hard to measure. So we use this visual occlusion method as sort of a surrogate for that. And basically what we're doing is, in this case, we have this moving target. We want them to, the task is keep the arm between these two lines all the time. If it exceeds that, the trial ends and you get kicked out. And what we tell them is, you only see the arm every time they hit a button. So try not to push the button unless you need it. But whenever you want to get a visual representation of the arm, hit the button and you'll get a blip of feedback of the red arm that shows up. And what we're measuring is the visual demand, which is basically the inverse of the amount of time between button presses. And this is something they use in driving sometimes. So we're trying to see, did people's visual demand go down when we put the skin stretch device on compared to the feed forward case? And indeed, it did. Just to give an example, this is a trial that the targets are stay between the blue lines and the arm position is the red. And we can calculate the visual demand at any time step. And with the skin stretch is the red line here, and you see it was pretty consistently lower than it was without any feedback, so they were using the information. This is the aggregate results. So on average, we reduced the amount of visual feedback required by about half or so. And the individual subjects are on the right. So they all decreased save one, which was basically flat, who didn't seem to be using the feedback much. So I'm jumping around a lot, but I'll kind of pause and take a breath there before I switch to a different kind of prosthetic application related to prosthetic sockets. So one of the common issues with a lower limb, so we talked about upper limb before, switch gears to lower limb, which are much more prevalent. A common issue there is the comfort at the interface. So essentially, when I'm walking around, I have this tissue on the bottom of the sole of my foot, which is well adapted to absorbing full body weight forces, right? When you've had an amputation, now I'm going to transfer that load up to some tissue that was never designed for that. And I'm going to have to try to make an accommodation to allow those loads to be transferred in a way that's reasonably comfortable. But that's a problem for many reasons. In particular, the limb volume was not constant. Some people have very short residual limbs, long residual limbs. There's all kinds of challenges associated. Even in the course of the day, as you walk on the limb, you can gain or lose volume in that limb, and the shape changes. So it's not just volume, but often shape. So we worked on this problem for many years in terms of, A, can I measure the fit? Can I measure how well the socket is fitting over time? And B, can I adapt as it changes if necessary? And we've done a few prototypes of different devices. So the first thing I'll just mention is in the picture on the upper left is a prosthetic liner that goes inside the socket that uses the same sensors I showed in the insole previously. Here we put in a prosthetic socket liner, and we can measure pressure and shear forces. The shear forces is what's really novel. There's really only been a handful of studies, and that's being generous, in the history of prosthetic sockets in terms of what are the shear forces in a prosthetic socket. A lot of pressure. It's relatively easy to get pressure. There's limitations even with the data that have been collected on pressure. But shear, there's very little data. I think, if I remember right, 13 people total maybe ever have had their socket instrumented with and maybe there's more in recent years, but at the time we did this, it was a very small number. And so there's a lot of value in being able to provide these data, and that's an example is shown on the lower left. And then some prototypes on the right of bladder-based systems that could actually make accommodations if we measure a shape change. We could insert some volume. This is an early prototype. In our more recent ones, we actually put the bladders in the liner itself. It's much easier to modify a liner in our experience than a socket. Sockets are all custom fit and require a lot of maintenance and TLC to sort of create and maintain. Liners are a little more standard and still many sizes, but at least not custom. Let's see. One current project I wanted to spend a little bit of time talking about is a collaboration we have actively ongoing with Georgia Tech. And I apologize, there's a lot of words on this slide. So Sandia is a Department of Energy laboratory. We work on a number of different applications for all kinds of government organizations. But our primary customer is the Department of Energy. There's a number of offices within the Department of Energy. I think the second biggest is called environmental management. So environmental management is responsible for the cleanup of all these and remediation of all these Cold War facilities and nuclear waste storage and all these complex, challenging environments where you've got people going in and all kinds of PPE to protect them from external hazards. But what we're not doing a good job of is protecting them from internal hazards. So the injury associated with often the PPE that they wear is causing them different kinds of injuries, right? So to protect them from external, chemical or other kinds of hazards, they might wear a SCBA tank with a respirator. And now I've created a new load on their musculoskeletal system, and they're at risk of a different kind of injury. And so we've been working for a few years now with the Department of Energy Environmental Management to look at, can we use some kind of wearable technology to mitigate the injury risk for these workers? And Professor Sawicki and Young and Mazumdar are collaborating with us right now to, as well as the other organizations you see on the slide here, are working to test and develop systems that we hope can address some of these challenges. So just two quick examples. This is at one of our large waste processing facilities in the DOE. These workers wear these full-face respirators with SCBA tanks on there that weigh 20, 25 pounds. They have basically a 1-hour shift maximum because that's how long the tank lasts. And a lot of them are just standing around for a lot of that because they've got somebody doing a job and 2 or 3 people have to supervise. And there's just a lot of ergonomic load. They monitor their heart rates to make sure that they're not overexerting themselves. So that's one type of task that is challenging. Other types include these blankets. They look like little tarps. They actually weigh 100 pounds or so. They're these lead shielding blankets for radiation shielding, and they have to go in and load these and then unload them, and it's not great for ergonomics, as you might expect. So we've been looking at a number of different applications. Some of the ways we're doing that are shown here. So as you can see, we've replicated the SCBA situation in our lab at Sandia, and we have kind of a poor man's version of the lab you have here, where we have a treadmill and a motion capture system and VO2 measurement for metabolic consumption. where we can test, have people do these tasks with and without the wearable technology and make some assessments of its merit. This is a study that's being done here at Georgia Tech currently with, in their lab that's similarly looking at some of these, simulated load carrying situations. Some of our other partners at FIU looking at these glove box operations, which also have ergonomic challenges associated with them. Some of the nuances we're looking at here include a lot of these devices have been developed, but there's some commercial devices out there that we're looking at for this. Most of them have been developed for like automotive or retail industry and application. They haven't considered things like, is it compatible with this PPE that DOE people have to wear? What if I take it into like a radiation environment? Can I get it out? Can I decontaminate it? Is it disposable now? Is it waste now? All these other issues that have not been considered. We're trying to look at sort of these DOE-specific relevant to see if we can apply some of this technology that's been developed for other industries for the government, as well as, if not, what needs to be developed, right? So there's going to be limitations of these commercial systems. When we can identify those with some specificity, we can make some recommendations about how to proceed. So just some examples of devices that are out there. Some of those exist here at Georgia Tech. Ankle assistive devices from a company that's spun out of MIT. This device spun out of NASA. It's a grip assist device. It's commercialized by a company called BioServo now. Lockheed Martin bought a Canadian company that built a knee assistive device. This HealWear device came out of academia and is now spun off into a company that's a back assist lift device. There's a chairless chair that we're looking at, which basically, if you're not walking very much but for some reason can't have a chair, which there may be a few situations like that, this is a device that you can buy now. And then there's some other sort of passive spring-loaded devices on the market. These are some examples. There's dozens of devices you can buy and hundreds more that are sort of being developed, and we're trying to evaluate those before developing our own, although we're also doing a little bit of that in parallel. So that's a very exciting active project. We've had very good collaborations with Georgia Tech on that, and that's scheduled to continue for many years to come, and we're very excited about it. So to wrap up, I just wanted to mention sort of the broader picture of what we do in robotics at Sandia, since I gave you kind of a narrow view of that. We've historically done all kinds of hardware development. You see, Ani worked heavily on the biped robot for the DARPA Robotics Challenge, shown on the upper right up there. Some custom mobility platforms for mining and other type applications. On the bottom right is a hopping robot that we developed that was licensed by Boston Dynamics that can hop with pretty good precision over pretty high distance, so it can drive around and then jump into different situations. We do a lot of UAS work these days, UAS and counter-UAS type research. That's a very active program. A lot of custom hardware. This is a robotic hand that we developed for DARPA several years ago that was low cost and dexterous. And then we do a lot of what I would call sort of high consequence automation. So that might include demilitarization type of applications where I got to take apart munitions. I don't want people doing that, but it also you don't want it to blow up. And so, we will take commercial technology and sort of integrate it with some custom things to do that. Also bomb disposal type applications. We've done a fair amount to work with law enforcement and other agencies for those kind of robotic applications. So I can't really talk about all those areas, but I wanted to give you a little bit of a taste of sort of the spectrum. Currently, we're doing a lot of autonomy work in the sense of algorithms for mapping and heterogeneous swarm type control for a variety of applications. And of course, there's a lot of ways to work with it. Sandia has, I think, 5 academic alliance partners, of which Georgia Tech is one. And so we like to work with Georgia Tech when we can. And there's of course many ways that can happen. We have internships and postdocs and staff positions posted, all the time in different areas. Robotics is kind of a modest size, so those tend to be a little bit fleeting. We have probably 100 or so people in robotics, just to give you a sense of kind of the scale of that, maybe a little less these days. And we also work with universities for a variety of reasons. In particular, for the work that I do, we do human studies, but we don't do some kinds of human studies or things of that nature. Or there's also many other areas we just don't have the right capabilities, and so we tend to lean heavily on academia to meet our mission needs when our capabilities just aren't the right fit. So we do that pretty extensively, and as I mentioned, we're doing that right now with Georgia Tech. There's no way we could have built a lab that replicates what you have here, and so we really do take advantage of that when we can. So that's kind of a very quick whirlwind overview of, there's many people that I didn't have time to mention in the talk that I did want to at least acknowledge that contributed to this work. So I'll go ahead and pause there and take some time for any questions or discussion. Yeah.
You showed a bunch of, I'm wearing too many masks. You showed a bunch of examples of wearable devices that are in development. Are any of these deployed for daily activities in any circumstance, or is this all still pre-commercial development?
So I'll say a tentative yes. Some of them have been deployed. The scale of which is a little hard to determine sometimes. We know that the automotive industry in particular has purchased a lot of devices, and we think, Toyota, Honda, BMW, at least, and I'm sure many other, Ford, have deployed these passive devices for mostly like undercarriage work. I think that was sort of the predominant, to reduce shoulder injuries, is people are holding a tool above their head all day. Some pretty low-hanging fruit to just hold their arms up, and so they have a backpack type device that provides shoulder support. So that's the most common. And then there's a handful of others. A bunch of retail organizations have looked at these lifting devices. I know Lowe's and Costco and a few others have done some pilot type studying. I've not seen them widely distributed at this point, but in the factory type environments, I think they at least are present. How prevalent they are, it's hard to know. I'm hoping to find out a little bit more about that, but it's still, I would say, fairly nascent in terms of applications. Other questions? Yes, please.
For the knee adduction moment, biofeedback works. Do you have any idea or sense of kind of the cognitive burden associated with that? So they could, reduce the knee adduction moment when they're paying attention to the feedback, but in like a real-world deployment situation where they're walking across campus per se, do you think they can do that kind of without active attention?
So it's a great question. My personal opinion, just my opinion, is that probably the best application would be some initial training that's sort of a high cognitive demand like on a treadmill or something. And then in chronic use, it would be more like, let me know when something's gone wrong, more than like, give me feedback every time. But I've developed a gait pattern now. In fact, we at one point came up with some kind of wonky concepts of like, we just want to stick a pebble up in their shoe. You know how annoying that is, right? Like when they're doing it wrong, just cause them some annoyance so that they stop doing the thing. Because you have no sensation in your knee, so you're beating up your cartilage without knowing it. Can we annoy them in some other way that gives them incentive to, but only when they've sort of strayed from what we want them to do. Other questions? Yeah.
Does knowing everything that you know about like walking and the kinematics and the dynamics and all of the issues that go along with it, does it make you overthink when you walk?
Shockingly, no. It probably should, don't you think? I mean, whenever I do think it kind of breaks your brain a little bit, right? It's like, how all the things you're doing under the hood. I think if you thought too hard about it, it might. But, one of the things that, studying this has caused me to appreciate a lot more is just how well adapted the human body is for a diversity of tasks, right? We think, oh, we're smart engineers, we know how to build robots to do all kinds of fancy things. It makes a lot of sense to just stick this device on a person and clearly it will do what we think it'll do, and then it almost never does, right? And that's because we don't understand the physiology especially the neural component of that, as well as we sometimes think we do. And also just, it's really hard to beat sort of that natural physiology. So when it comes to, prosthetics is an easy example. If I've lost my limb below the knee, for instance, I can build you've seen these bladed runners and stuff, and go pretty fast, right? You don't want to walk in those limbs. If I'm doing one task, like running, I can design a system that's pretty well adapted to that specific task. I have a foot that's good for walking, I have a foot that's good for running, I have a foot that's good for climbing or snowboarding or whatever. But what our feet are good at is all of those things it does all of them pretty well, right? And what we have not been able to do from a technological perspective yet is really approximate that versatility. And that's why the upper limb is such a more difficult problem in my view. Upper limb prosthetics are, very crude relative to, lower limb, there's still issues with them, in particular the comfort and some of the other issues, and versatility. But like I said, you mostly just walk on it. The arm, it's really, people have struggled for decades to try to come up with a prosthetic arm that is close enough to the physiological arm that people say, yes, I want this, versus just literally nothing. Which if they're bilateral, they'll usually take something. But if they've just lost one arm, they'll just try to get by with the other. It's a good question.
So you showed some really cool thoughts about joint level mechanics, like the spring-like behavior. Can you talk a little bit about how you could use some of the analysis or techniques to design just robots rather than assistive devices?
Oh, right. Yeah, for sure, and you know some about this, of course, but I think, if you say you're designing a walking robot, and you want, one way to do that is sort of an anthropomorphic way, is to, let's say, we know people who are good at bipedal walk. We know an animal that's good at bipedal walking. What can we learn? And so in that case, for instance, many our biped walking robot, which I didn't talk much about, was specifically targeted on efficient walking. So cost of transport is sort of the thing that is the main metric that's, so you've seen these like Boston Dynamics robots that can do parkour and all this kind of crazy stuff, right? They, even just walking, they'll run out of battery within an hour typically, right? They tend to be pretty power hungry. So say we wanted to walk long distances or long periods of time, how could you do that? You want to use as little energy as possible, and one way to do that is to leverage the dynamics of the system. And so when you look at a system like this in the ankle, you say, well, I clearly should just put a spring in the ankle and reduce the amount of motor force I need to use, right? That seems like a fairly obvious application. You can do something similar with the hip. The knee, if you look at the knee, actually tends to absorb a lot of energy. It's fairly neutral from an energy perspective in most walking situations. So when I say absorb, what that means is the joint velocity and the torque are in opposite directions, right? So the power is negative. So what that means is the muscles are absorbing energy around the knee, and then they will produce it again as I kind of go to straighten my leg again. But there's a lot of energy absorption that goes, and so people have said, okay, well, why don't we put something on the knee that actually harvests energy? And either I can release that at the ankle, or I can power my phone with it, or I can do other things. And there's some challenges with that, but people have tried to do it, right? And so if you study these joint functions and say, okay, what does the energy and force distribution look like at a joint, I can often make some pretty interesting inferences about what can I do on a person, what could I do on a robot that would allow that robot to be either efficient or high performance. So I think there's a lot to learn from the physiology. This is obviously mostly your Achilles tendon at play here, right? That's loading up and releasing. But in a robot, you could do something much, you just put a rotational spring in the ankle and it does kind of the same thing. It's a good question. Yeah, Greg.
On the insoles that you guys have, is there anything about the design that makes those not calibrate well and surfaces are solid?
Yeah, there's a lot. Yeah, we haven't done non-standard surfaces yet. I mean, we have a very limited funding for that, unfortunately. The calibration of those is a little, right now we calibrate them on a force plate, right? And so we have a model, we have all these sensor signals coming in, and we can pick sort of, do we want the raw signals or some processed version of those? And those go into the model, and then the thing we train on is the ground reaction force and the COP coming out of out of the force plate because we're not trying to do sort of purely analytical calibration at this point. And so one of the big questions is, if I calibrate on person A, does it work on person B? Or if I calibrate on person A, B, C, and D, can it work on person E? And that still is really, I think Ani and I have done it. I'm not sure, and maybe one or two. It was developed for a prosthetic application, so we've actually done it on the under a prosthetic foot and under an intact foot. And so we have some data on that, but it's very premature. I wouldn't draw any hard conclusions from it at this point. So really, one of the things I'm very interested in doing is playing with that calibration model and just trying to figure out what are the right parameters, what's the right structure of that model. Is it linear, is it nonlinear, is it, could be a neural type model or just a straightforward regression type model. That has only been explored, no offense to Ani, who did a lot of that work. It was only explored at a cursory level because that's all the funding we had to do it, essentially. But that's all, there's a lot to do there to really, so that could be good or bad. We get decent performance without having spent a lot of time on those things, so I think there's room for improvement. But also there's a lot of open questions. Yeah.
You mentioned compliance and adoption for these devices, specifically relating to upper limb devices. What are the key design considerations, and how will you come about determining what those are for compliance? Is that based mainly on biomechanics and engineering, or is that based on human factors and interacting with the applications?
So people have tried to answer that question, and I'm not an expert on it, so I'll talk around it a little bit. But it's certainly a combination of all of those things. But what's often neglected by us engineers are those second things you mentioned, those human factors and comfort. And so when I got into prosthetics, many years ago, I came as a roboticist, came into this as, well, I want to design cool robot prosthetics. That was sort of the notion. And then if you spend any amount of time talking to amputees, which you should if you're going to do this kind of thing, talking to amputees and prosthetists and other clinicians, you quickly realize that's not what they need or want. What they need and want is something that's more comfortable and something that's easier to take on and off and easier to clean and all that. So that is the feedback that, and there have been surveys on this. Why do you use it? What do you like most? What do you like least? Why did you reject your prosthesis? All these kind of things. And depending on the framing of those questions and there's the subject pool, you get different results. But often, I think from an engineering perspective, we would underestimate how much those soft things matter, for lack of a better term. I think if you want to be successful in these kind of fields, the more time you can spend with the wearers and the users. So in our DOE, I'll kind of switch gears, talking about the DOE application, we spend hours talking to the union representatives that are associated with these things because there's regulatory issues associated. We spend time at these sites talking to the workers. We put the equipment on that they wear. You really do have to get into the weeds of the users if you want to be successful. And so there's certainly engineering challenges, but even if you're great at all of those and you neglect the other, I don't think you'll be successful. That's a good question. Thank you. Any other questions? Yeah.
So the liners with the bladders you mentioned for the amputees, was that focused specifically on just transfemoral amputees or also like transtibial?
It was primarily transtibial. So it could theoretically work for both, but we only tested it on transtibial. So we specifically put the bladders in locations where you tend to lose volume, right? So without going into too much detail, you've got this anterior tibia right here, which is generally no soft tissue right there. You can probably almost hear that. There's just a thin layer of skin. Usually there's force applied on either side of that. And this is one of the areas, this tibialis anterior muscle right here is where people will lose volume. And then they lose a lot of volume on the posterior side, on the soleus and gastrocnemius muscles, which are now tied off and not functional on these soft tissue areas. So we put the bladders in those locations. But on the transfemoral, it would be, I think, a little more, there's a little less variation in terms of, it's a little more soft tissue everywhere. And so you'd probably not have to be quite as careful about the location of those. But with the transtibial, we did place them anatomically on purpose in areas we thought they would lose volume.
Any other questions?